He was miserable. He was out of school for a week. I slept all weekend. So I had to listen to it from my wife, but that was about the end of it. I was missing time. Okay, so matrix addition is really just a matter of adding corresponding parts, as you know. All right, so, and I say as you know because it's the kind of thing that I think would be common sense. You know, it was like that when we were doing vector addition, so why would it be any different for matrix addition? But it does require that the dimensions are the same. Dimensions have to be the same. If they're not the same, you can't perform matrix addition. All right, but that's also along the same lines of common sense that I think that you would come to expect, because how are you going to add two vectors if they don't have the same dimensions? So in this case, it's 1 plus 5 is 6. 2 plus 7 is 9. 3 plus 2 is 5. And 4 plus 0 is 4. All right. And so one of the big questions that we're going to get, or at least come to wonder, I suppose, would be, well, what do you get when you add two matrices together? Like, we know what we get when we add two vectors together. What do you get when you add two matrices together? All right. Well, it depends on what the matrix is representing. If a matrix is representing the column vectors of a system, then what you're doing is you're performing vector addition twice simultaneously, and you're getting the result pretty quickly and relatively easily, I guess. So what we're looking at is the sum of the vector 1, 3 and 5, 2, giving us 6, 5, as opposed to the vector 2, 4 and 7, 0, giving us 9, 4. All right, so you just kind of look at a matrix as sort of like a clearinghouse for all different vectors. You know, if they have the same dimensions, you can create a matrix whose columns represent the vectors of a system. That's one application of matrix addition. But there's a bunch of other possibilities, and when we get into the word problems a little bit in more detail, when we get to Markov chains and the Leontief input-output model, you'll see what I'm talking about. But as it stands right now, a matrix represents something. The columns and the rows have meaning. It's just a question of what is that meaning. All right. For our purposes so far, they represent the vectors in a system. All right. So the example, I gave a solved example there just in case you wondered what a 2 by 3 added to a 2 by 3 looked like. I didn't think it would be necessary to bore you with the arithmetic on that. You could also put this in your calculator and let it do the math for you. I didn't think it was necessary to do that either, just because adding corresponding parts is not difficult. Now, if one matrix is made up of some funky fractions and the other had some radicals in it and stuff like that, then maybe you let the calculator do the heavy lifting. All right, shorthand notation. This is going to become more important as we go on. So far, it hasn't been overly important. We can represent an arbitrary arbitrary entry of a matrix A by designation A sub ij. All right. Sometimes I have a comma separating the I and J, but we could also just write it as A sub I J without the comma. All right. Because if you have, I mean, you could see I have the m by n matrix, so that would be like a finite matrix but very large values potentially. Like, you get out of hand, I mean, you start adding the commas that you'd have to include in there. It takes up space, it takes time. You just don't want to do it. So instead what we would do is write A sub 11, but it doesn't really mean 11, it means 1, 1, where we're talking about the ith row and the jth column. All right, so that first entry, for example, And, you know, it's all detailed there, but I figured I'd kind of spell it out for you. Or at least have you spell it out for yourself at some point. So this is saying the term, or the entry, if you want, of the matrix in row 1, column 1. All right. But when you have a repeated value, it doesn't always necessarily tell you what you need to know, because you're like, well, which one's row, which one's the column? It's always the first entry that's the row. But if you're worried that you're going to forget that, then select something that doesn't have a double entry. And so this would be row 2, column 1. When we start getting into the idea of the determinant, it's going to be very important that we keep track of what's what, all right? And so having really a naming convention, you know, some standardized approach for naming the entries of a matrix, that's going to become really, really important. It doesn't seem like it would be necessarily important. You look at it and say, how on earth could that possibly be important? I promise you, it's going to be the kind of thing that is like fundamental to your understanding of the derivation of the determinant process, all right? Because we're going to have to figure out all different possible arrangements of values within a matrix. It's fun, but it can be a little intimidating if you don't have a particular scheme behind you. So, you know, I said to revisit matrix addition. I just wrote it using the notation form. I don't think this adds anything to the party, because you look at it and say, okay, well, yeah, that's telling me to add the corresponding parts. But what it's really saying, if you kind of decode it, and just bear in mind that the thinking comes from the notation form. Like all these words and these explanations, they come from the idea that the notation exists and is understandable. And because of that, you're able to decode it and make sense of it. So this is telling me to add the row 1, column 1 of matrix A to row 1, column 1 of matrix B. All right, that's the recipe. So it's not like the process is leading to the notation. It's more like the notation led to the process. All right. So in this case, is it really necessary? Probably not, but it will become necessary. It's row 1, column 1 of B, because you see the entries here are all A sub 1, 1, A sub 1, 2, and so on. And then the second matrix is all B sub 1, 1, and so on. So it's implied that this is matrix A, and this would be matrix B. As mundane, boring, tedious. You throw in dumb, annoying, idiotic, any of those words to describe it as it might seem.
You said add row 1, column 1 to what?
All right. Scalar multiplication, we understood it for vectors, but you know, sometimes you just want to have that reassurance of knowing that what you thought was true is still going to be true. So if you have scalar multiplication for a full-blown matrix, you're multiplying every part of that matrix by that scalar. So anytime you perform an operation on a matrix, you're performing a transformation of some kind. And we never really want to lose sight of that, except, you know, when we start moving away from the third dimension and getting into higher order dimensions, things can get, you know, seemingly a little bit more abstract. But the reality is that we're building the framework and the foundation in 2 and 3 dimensions so that we can understand the mechanics of it, so that when we move into the 4th dimension, 5th dimension, and so on, we can rely on those processes. And scalar multiplication is one of those processes. All right, so what this is going to do, as far as the transformation is concerned, this is going to dilate it by a factor of r. Dilates the matrix, poor quality the, by a factor of r. All right. Now that could be getting bigger, or it could be getting smaller, but depending on what the matrix represents, that could be a very visual thing. Now, we'll see some instances where a matrix, while it could be represented visually, that visual representation is not going to have much meaning. Like you're talking about weights in a course. In this course, I forget, honestly. I know that tests are like 40%. That's why I make a syllabus. I think that's why they make us make syllabi, so that when we come up with a grading system, we don't forget what that grading system is. Because honestly, it's like, I know there's one. It's written down somewhere. I'm pretty sure it's 40, 20, or maybe 40, like 15, then like another 10 for participation, and then maybe another 20 for like the final exam, something like that. It's got to add to 100. But the bottom line is each one of those percentages ends up being weights. So those weights could be scalars, right? And the vector related to those weights would be your individual scores or your averages in each category, all right? If I were to graph that, what would that graph, what would the visual representation mean? I got a vector that represents 40%. Cool. What does that mean? Who cares? Like, the visual doesn't have much meaning for us. All right, so you got to kind of pick and choose. But if we are dealing with having columns that represent the vectors of a system, then each one of these vectors will have been dilated by a factor of r. All right. So that brings into the process the idea of a transpose and the overarching theme of this, where, okay, a transpose is telling me that I could swap rows with columns in a matrix. And there are a whole host of properties associated with that, which is great, because properties are good, except when you have to memorize them and take like a multiple choice test or something like that related to them. Those suck. I don't like doing those. I don't like doing them as a teacher, and I don't like doing them as a student. So that's not going to happen. But, there are properties that you could rely on which make this a valuable process. The question would become, under what circumstance would I consider taking a column of a matrix and making it into a row? Like, okay, well, that's kind of strange. So let's talk matrix multiplication. I'm just going to kind of go back for a second. Vector multiplication. Let's say I wanted to multiply. I'll just come up with a simple vector in 3 space, like 1, 2, 3. And I want to multiply that against 2, 1, 4. Now we know this as the dot product. Now we also know the dot product is some magical set of rules or processes that allow us to perform an operation, and it gives us a meaningful result, but then the question would become, well, what on earth allowed us to do this to begin with? All right, because if I'm taking a 3x1 matrix and multiplying it by a 3x1 matrix, vector multiplication falls apart. All right, this doesn't play out. If I try doing this on my calculator, it's going to give me an error message. All right, so this is no good. But what I can do is rewrite my first vector as 1, 2, 3, make it a row vector instead of a column vector. And then multiply that against 2, 1, 4. The rules of matrix multiplication are going to work out just fine here because I have a 1 by 3 matrix against a 3 by 1. So the result is going to be a 1 by 1. All right, so it's this concept of the transpose that allows something like a dot product to actually happen. Dot product is a shortcut to finding the transpose of a row vector, column vector, making it a row vector, allowing you to perform vector multiplication using the appropriate laws of linear algebra. So when you do that, you're looking at 1 times 2 plus 2 times 1 plus 3 times 4, and so 2 plus 2 plus 12. That's going to be what, 16? Honestly, at that point, it didn't even matter what the answer was. It mattered more that we could get an answer. One way we couldn't, the other way we could. But it's the properties behind a transpose that allow us to do that to begin with. If the properties that I'm going to introduce you to in a few minutes, if they didn't exist, then this would not be something that could be done. And so therefore a dot product wouldn't exist, and then we wouldn't have a convenient way of testing for orthogonality, and then we wouldn't have a meaningful way of figuring out the angle between two vectors. All this stuff would fall apart, right? But outside the context of vectors, what would be the benefit of swapping a row with a column? The short answer to that, context. You have a situation. Some situations allow for you to do that, some don't.
So swapping a row with a column, would you call that like transpose?
Yep.
Or is it
The transpose of a matrix is
okay? Is
exactly the same thing as doing that. You're taking the first row, the first column, and swapping it with the first row. Second column with the second row, third column, third row, however many there are.
Right. Is there like any condition on it? Like,
Well, you could always do it. It's just a question of whether it's beneficial to do it.
oh,
And when we get into the properties, you're going to see under what circumstances it's beneficial to do that. Now, if we have a symmetric matrix, then A and its transpose would be exactly the same. So in that case, you're looking at that beautiful symmetry that exists only under certain circumstances. But that's telling me that my row vector and column vectors are exactly the same. So that's a kind of cool occurrence, but that's not something you could always count on. All right. So the example that follows is really just performing operations. So I'm going to put a star on that. Oh, and I will just point out to you very quickly, because for a 2 by 3 matrix, I don't know that you need to get your calculator involved to do a transpose, but if you go into the matrix menu, you see that there is a transpose function. It will find the transpose of a matrix for you. In most cases, it's usually a situation where you don't actually want to just, like, a question is not, I'll tell you this right now. There won't be a question on a test saying, here's matrix A, find the transpose of matrix A. You're doing it for some other reason. So you're finding the transpose of A so that you could then multiply it by B. All right, so if that's the case, having matrix A in your calculator, knowing that you can just signify that that the transpose of A is being multiplied by matrix B, and have the calculator do all the work, that's really nice, because odds are you need matrix A for something else. All right, But that's in here. It's option 2 on this version of the calculator. I'm pretty sure it's option 2 on the other one also. Let me just double check. Son of a gun heck. Yeah, it's option 2. Yeah, it's just like a little capital T in your calculator. So you put in matrix A, you select that little t, and you call it up. And so it's pretty straightforward. So this next little bit is me just kind of formally stating what I was talking about before. And what we are looking at is the dot product or the inner product when we're multiplying two vectors. It's just one of those vectors has to be represented as a row vector. All right, so I personally didn't think, I mean, I typed all this up. Well, I copied it from some source online and then I retyped it to make it look not stupid, which usually means that there's probably a typo or 7 in there somewhere, so be on the lookout for that. But as I was reviewing my notes, I looked at it and I was like, you know, I don't think this really gets the job done in terms of an explanation, so I think my little side example is the way to go. But the matrix multiplication is really just taking that idea and expanding upon it. So matrix multiplication is really us performing vector multiplication repeatedly throughout one row, one set of rows of matrix A upon the columns of another matrix. So the idea is, what is the meaning of each one of these rows? You know, context is going to be the deliverer of that information for you. So, you know, that ends up being dependent on the situation. So we're still kind of in the skill building phase of things, but we'll see where this is all going. You know, I got some cool derivations down the line where I could show you how things like correlation and regression came to be. You know, in my Calc 3 class, I derived that using partial derivatives, and show them how to go through that process of coming up with the formulas for finding linear regression and correlation. And I'll show you a completely different approach here that'll do the same thing, but based on the skills that we cover in this class. Right? So it'll all come back to context. All right, so this is along the same lines. So I'll just put stars on these. Because again, I don't think we need a whole class of me just showing you how to multiply matrices. If anything, all this really serves as is a refresher. And so try it on your own, and next class we'll go over it briefly. And if it's still a little iffy, then we'll take some more time and discuss. All right, but that's really the genesis of it. I need water. Get a cough drop too. Of all the things that happen on Flash Night, it's crazy. It's going to be a good episode too. Setting us up for Crisis now. We're ready to rock and roll. I'll be coughing through the whole thing. Then Arrow's coming on right after it, and that's going to be all the last season of Arrow's all Crisis all the time. So I'm just not emotionally ready for it. All right, so I just can't get a word out. It sucks. So these questions aren't really so much about you demonstrating the ability to multiply. They're more so about you demonstrating the ability to recognize when multiplication is something that can happen. All right, so in this case, what I'm looking at in number 1 is a 3x1 multiplied by a 2x1. All right, so with that in mind, we're not looking at something that's structured appropriately. All right, so the number of columns in the first matrix has to be corresponding with the number of rows in the second matrix. So I want to see if there's some kind of adjustment that could be made here in order to allow this to happen. And any kind of adjustment is going to be sufficient. Because again, these are out of context. So it's a question of, I don't know what this is used for. So what does it matter? Like if the multiplication is not precisely symmetric, that's okay. It's just the idea of getting used to the skill. All right, so let's say I leave the 3x1 as is. What I would want to do is make this a 1x2, which would then yield a 3x2. All right, because the number of columns in the first matrix has to correspond to the number of rows in the second matrix. All right, so then this would be a rewrite of 2, 6, 1 against 5. I put a comma there all of a sudden. 5, -1. All right. Now this little side work that I did of determining the dimensions of my answer, you absolutely do you absolutely need to do that? Do you have to show that work? No. Because the reality is, if you put it in your calculator in the right way, it's going to give you the answer. I'm not going to know any different. But if you're doing it by hand, I personally would like to know what I'm aiming for. I'm aiming for a 3-row, 2-column matrix. So it tells me what I'm up against. So 2 times the 5, 10. That first entry is easy enough. Now the second entry, okay? So this is A sub 1, 1 and this is B sub 1, 1. When you multiply them together, A sub 1, 1 multiplied by B sub 1, 1 should give you AB sub 1, 1. Not because they actually match each other, but because we're looking at the merging of the two ideas. So the first row, because again, it's still the same idea as what we were dealing with before. A 3x1 against a 1x2 becomes a 3x2. The inners, as long as they match, are good. It's the same idea here. So if the next one is A sub 1, 1 against B sub 1, 2, so I could just kind of chuck that in here somewhere. It really doesn't matter where, I'll just kind of reduce it. This guy here is B sub 1, 2. I can kill this, I don't need it anymore. We'd be looking at A sub 1, 1 times B sub 1, 2, which would give a result of AB sub 1, 2. All right, again, with the idea that I'm taking the first entry in the subscript and the last entry in the second subscript. So it's giving me a recipe of where my answer should go. Now, do you need to know that, notation-wise? Well, probably a little bit more than you did for the addition, because a novice, a person not having never completed any of these kind of multiplication problems before, wouldn't necessarily know what the scheme would be. All right, so it seems now that I'm putting my results across each row and then working row by row. So across and then down. All right, so this is giving me the justification of why the next entry, which would be -2, yeah, is going to go in this position and not anywhere else. All right? Now, you wouldn't have to denote that for every single possibility, but you should at least take it into account when you're doing this. So the next one, common sense would tell you that we're working row by row now. So 30 and then -6. 5 and -1. But again, I don't need you to do these problems to demonstrate that you can multiply. I don't even need you to multiply. Type this into your calculator. All right, so you tried multiplying it the way it was here. It didn't work. All right, try multiplying the transpose of one of them by the other one. Oh, that didn't work. Eventually, you're going to come. You're looking at. Let me see if I can figure this out. Those are just 4 possible arrangements. Yeah, if you're doing it in this order, current form or the transpose against the original, or if I keep this one as is, current form of the transpose of the second one. So 4 possible ways in which I can trial and error my way through this. All right, so let me actually just do that for you one time just so I can check it off my bucket list, I guess. I have a very simple bucket list. I came to the conclusion a long time ago, I think my wife is trying to kill me. I say that because I have a white knuckle fear of flying, and she seems to want to put me on the longest possible flights that exist. So this summer we went to Indonesia, and so we had a solid 24 hours each way in transit, and so my bucket list is never going to involve traveling. Like when I get to the end of the road, it's going to be like sitting at a park bench for an entire day, like day after day. Like maybe just somebody drive me off, drop me at a park bench. I'll sit there and just drool all day long or something. I don't know. Very simple. I like to keep it easy. So 5, -5, -1. All right, so I have my 2 matrices in. Well, calling them matrices. They're clearly vectors. It's just a question of, like what I'm treating them as. So when I try doing the simple multiplication, I do A times up. Let me get out of here. First, let me make sure I didn't just screw that up. Names, matrix A times matrix B. I hit enter. It says error dim mismatch, dimension mismatch, meaning that the number of columns did not match the number of rows in the way I had it originally structured. So what I would do is just go back and say, okay, well, let me try the transpose of one of them. So the transpose of matrix A times matrix B. Dim mismatch. All right, so that didn't work because what that would do is it would create a 1 by 3 against a 2 by 1. It's still not matching column with row. All right, so then I would say, all right, well, what if I did it the other way around? Then all of a sudden it works out beautifully. All right, so the act of actually performing the multiplication, you can brute force your way through it, but the key ingredient, I'm satisfied if you get the answer in any capacity. If I ask you to come up using row vector rules for computing AX, if you come up with any answer, I'm satisfied that you understood the concept of a transpose because it's the only way it would have worked out. All right? So you had to have. Unless you were sitting there, I mean, you must have really great eyesight in order to be copying somebody else's matrix work off of, their papers. That's generally not happening in this class. I mean, in an algebra class, if people had like an answer that kind of popped out of thin air, I'd be like, all right, who'd you cheat off of? But in this class, I mean, it's a different story because there must be some calculator work that went into play. So anyway, this is weird, by the way. Why is it like floating? Did I just not put it in the corner? I got a floating calculator now? It's like these things update and then it's like, hey, guess what? We got an update for you, but we're not going to tell you anything about it.
Well, you can go to the website and read about
That's insulting. A website and read. How dare you? I shan't be doing any such thing. Yeah, I suppose I could. So, the next one's along the same line, so I'll put a little star on that.
Do you want to transpose on this one because it's a 3 by 2, like, and 2 by 1, so
Nah, so you just put it right in, yeah. So you're good. So you get the concept, so that's the idea. All right. So the example that follows, construct a 2 by 2 matrix B such that AB is a 0 matrix. Use 2 different non-zero columns for B. All right. So, we have some notations down here, but the important one, AB equals 0. It's not necessary that A equals 0 or B equals 0. All right. So what that's telling us is through the process of matrix multiplication, you can get the 0 matrix without either part of them being equal to 0. So this is where, and I would even put a star. I mean, if you have a highlighter, go for it. But I clearly identify this one. I mean, the other ones are important too. I mean, Roman numeral 2 is pretty important. I mean, because that's kind of counterintuitive. If AC equals BC, you would think, I mean, ordinary algebra, you would think that A and B would be the same as one another, but not necessarily the case. But this is the one that we're focusing on here. It's not necessary that both that either A or B are equal to 0. That's really kind of important because that flies in the face of pretty much all algebraic reasoning that like the zero product property from like all of quadratics. That was the reason why you could factor polynomials and then set each of those factors equal to 0 and then solve. Because if any or all of those factors equal 0, that would make your entire polynomial equal 0, given these are zeros of the function. Right? But what this is telling me is that's not necessarily the case. Right? Not for matrix operations. Which is news. I don't know if it's good news or bad news. It's just news. So AB equals 0. So we have 1, 2, -2, -4. And we have to construct a 2 by 2. So matrix B. So B sub 1, 1, B sub 1, 2, B sub 2, 1, B sub 2, 2. And the result should be the 0 matrix. All right, so we're starting to kind of sort of make our way into the world of factoring matrices. The idea that, okay, so we can multiply matrices, we're starting to get a little sense of the quirks that come into multiplying matrices. If there are quirks in multiplying them, then you could be damn sure that there's going to be quirks in factoring them. Bless you. All right, so again, as long as you know the conventions behind this, it's fine. You'll be okay. But notation-wise, this is the appropriate notation. But sometimes even I get lazy. You'll see in my answer keys online. Sometimes I just go E, F, G, H, or X, Y, Z, alpha, or just alpha, beta, gamma, delta, you know, like whatever. Just anything other than writing this, because I know I'm looking for 4 unique values. Well, maybe they're unique. Maybe they're identical. Maybe it's... I'm just looking for something that's not the 0 matrix. All right, so maybe it's the identity matrix. I mean, it's not, but maybe it is. You know, so it could be maybe the case that B sub 1, 1 and B sub 2, 2 are the same number. I don't know that going in. I got a plan for them to be different, but if they're the same, I guess I'll be informed, because I don't think I'll be happy, sad, or otherwise. I don't know what the otherwise would be. All right, so 2 by 2 against a 2 by 2 is going to give us a 2 by 2, so our structure is good. A sub 1, 1 multiplied by B sub 1, 1 is going to give us A, B sub 1, 1. All right, so that's telling me... oh, sorry, that's for vectors. It's more complicated with matrices. So, still in vector mode. We're going to multiply our first row, our first column. We're looking at 1, B sub 1, 1, plus 2, B sub 2, 1 should be equal to 0. All right, so we're just finding inner products every which way. All right, and that's one of the reasons why the dot product is also known as the inner product, because each step of the way we're finding products, but we're not finding the products of the entire matrix. We're finding products of just different components within. All right. So then row 1 multiplied by column 2. So dotted against 1 B sub 1, 2 plus 2 B sub 2, 2 is equal to 0. Row 2 against column 1. So negative 2 B sub 1, 1 minus 4 B sub 2, 1 is equal to 0. And then the last possibility would be negative 2 B sub 1, 2 minus 4 B sub 2, 2 equals 0. Now, full disclosure, properties that exist that we have used before are still fair game. Like, for example, scalar multiples and things like that. If I wanted to, I mean, I could consider maybe dividing everything by 2 here, negating everything, right? Maybe perform some row operations and things like that. That tends to muddy the waters a little bit, though. because by setting up these equations, what I created are two distinct systems of equations, each with consistent variables. Right? So if I solve the first and third set of equations as a system, and the second and fourth set of equations as a system, then I'll have the solutions that I'm looking for. All right? So that's what I'm going to do. But we had to get through the setup phase. All right? Because they're actually in the right format. We're looking at a homogeneous system. All right? So we have coefficients of 1, -2, 2, -4, 0, 0. Let me go with, I'll take that ugly orange. It's not that bad. 1, 2, 0. And so what I get from this is the idea that there's a relationship between these two systems. They're basically, what's good for one is going to be good for the other. All right, so I just got to go through the process of figuring it out. Now, going through the process is not going to be, I would say, it's not going to. I know it's not like possible to wash down whatever the problem is, but it's like right here, and I really want the water to just hit that part of it. It did not happen.
I have recall if you want, they help you.
It helped, yeah. All right, good. Thank you. These halls ain't doing jack. It's got like double wrapping. I didn't even know it's good. All right, so now we do some math, but you know, there's no real requirement that you do it by hand at this point. Well, although I would say that doing it by hand is not terrible. And in fact, if I just do a 2R1 plus R2, you're done pretty quickly and easily. So that's kind of nice. Alright, so it's going to be the same thing for the other one. Just different variables. So what we get is B11 is equal to -2 B21. All right, for the first system. Now, the other one's zeroed out, so all we can get from that is that B21 is equal to B21. All right. And then for the second one, we would say B11 is equal to 4. I'm sorry. No, I'm not sorry. I'm right. Shockingly. If I was wrong, I would be sorry, though. Oh, it's B22, though. And it's 1, 2. So I was wrong, and I am sorry. Just paying off that previous comment that I made. Just making sure I wrote some of that correctly. Okay. So, just cleaning it up a little bit further. Wrong color. B11, B21 would be equal to B21 times negative 2, 1. And then B12, B22, so that'd be the second column of my B matrix, would be B22 against negative 2, 1. All right. So what they're asking again is construct a 2 by 2 matrix such that AB is the zero matrix. What we just came up with is anything that satisfies this system is going to fulfill that requirement. They're saying use 2 different non-zero columns for B. All right, well, we got that covered. As long as B sub 2, 1 and B sub 2, 2 aren't themselves equal to 0, then we'll be in good shape. All right, so B sub 2, 1, if I define it as 1, so let B sub 2, 1 equal B sub 2, because I could let it be equal to anything. I'll just let it equal 1, keep it simple. Then B would be equal to negative 2, 1, negative 2, 1. But any scalar of that would do the job also. All right. And so you could test it out. I mean, I think we could just do it on a quick visual level and say 1, 2 against negative 2, 1. You're going to get negative 2 plus 2. That's going to give you a 0. 1, 2 against negative 2, 1, same deal. Negative 2, 4. No, I'm sorry, negative 2, negative 4 is going to give you 4 plus negative 4 in both cases. So that'll give you the zero matrix. And so depending on how we define our B1, B2, it could give us a wide variety of different possibilities. But as long as we came up with something that did not involve the zero matrix, we were good to go. All right. So there are other ways to do it, easier ways, yeah, sure. But this way involves the notation, and since that's kind of what I'm trying to get across as being kind of the precursor of what's to come, that's why I show it this way. All right. So that's at least a recommendation anyway. We've already learned all the skills necessary to do it. It's just a question of, all right, under what circumstance would an inverse be useful? But isn't that the case for everything? You know, like we're learning all these skills, like why are we learning? You know, and we'll apply it. We'll look at the graphs and we'll really kind of dive in deep and see what the story is. But for now, it's just the skill. So I will preface this by saying your calculator is fully capable of easily finding the inverse of a matrix for you without doing any of the stuff that I'm about to do. However, on the test, I am going to ask you to find the inverse of a matrix by hand. All right. So we're going to be bringing back our good old friend, row reduction. All right. But I'll just show you real quickly. So I have 1, 2, 3, 5. So 2 by 2 matrix, 2 by 2 square. So 1, 2, 3, 5. Quit out of here. Finding the inverse of the matrix is as simple as calling up the matrix. And you know how we go into the matrix menu by hitting second inverse? That x negative 1 key? Yeah, fun fact, don't hit second. That's your inverse. It'll do it for you. All right? So, yeah. That kind of sucks because knowing that it's as easy as that on your calculator, same thing with matrix multiplication, but yet you're going to have to do it by hand. It's just, why does this need to happen? But, you know, we also think about all the things that I let you off the hook with, and so you're kind of like, it's all right to do some things by hand every now and then. Right? So, in this rule here, the inverse of A multiplied by A is equal to I, and also the commutative property variation of that. That's nothing new. It just go back to basic algebra. If you multiply two inverses, the result is always equal to 1. That's the whole point. That's why it's called multiplicative inverses. And the I was the multiplicative identity. It's the same idea here. Right? So if I multiply inverse of A by A, the result should be equal to I. I just got to figure out what that other matrix is, that inverse matrix is, that when multiplied by A will give me the result of I. Well, there's a couple of ways I could do that. One way would be to do the thing that I just did on the previous page, which, well, 2 pages ago, whatever it was. You know, make a new matrix. You know, we could call it A sub, or inverse of A with values A sub 1, 1, A sub 1, 2, A sub 1, 3, no, 1, 3, geez, now I'm just making stuff up, 2, 1, 2, 2, and then perform your matrix multiplication, which again is just your inner products. So A times the inverse of A. 2 by 2 square matrices, it doesn't matter what order you do them in, it's going to be fine either way. We're going to be looking at A sub 1, 1 plus 2, A sub 2, 1 equals 1. Then A sub 1, 2 plus 2 A sub 2, 2 is equal to 0. A sub, 3 A sub 1, 1 plus 5 A sub 2, 1 is equal to 0. And then, yeah, Kev.
Isn't it A sub 1 plus 2A sub 2, 2?
Probably.
Second line?
A sub
2, 1.
2, 1.
Yeah.
This is getting multiplied by that. So 1, 1, and 2, 1. And then this is getting multiplied by that. So 1, 1, 2, and 2, 2. And then this is getting multiplied by that. So 1. I think it's right. Yeah, because it's getting multiplied by first row by the first column, 1, 1, and 2, 1. And then by the second column, so 1, 2, and 2, 2. And then the 3, 5 is getting multiplied by the first column, so 1, 1, and 2, 1. And then it'll get multiplied by the second column, so 1, 2, and 2, 2. All right, so we have this lovely looking system. just glorious. Really. Stunning, even. You can look at it a variety of different ways. You could just make up new words for it every step of the way. It's just.
Shouldn't it be 3A, 1, 2? The last one?
For the last one? Yeah, 1, 2, thank you. So we would go through the process, and I'll just kind of spoil it a little bit for you. We have 4 variables. It's really a 4-variable system. We could actually rewrite each one of these matrices, each one of these linear equations, so that it includes all 4 of the variables. We didn't do this with the last example, but we could do it and come up with an augmented matrix that's just glorious. it would be splendid. Right. The other option is a little nifty shortcut, which I'm actually going to prove to you next class as to why it works. Or what you can do is take matrix A and augment it with I. Meaning, rewrite matrix A 1, 2, 3, 5 and augment it with the identity matrix. All right. Row reduce this so that A goes down to the identity matrix. And when that happens, I will emerge as the inverse matrix of A. All right, so what's going to end up happening is you'll get a new matrix through the reduced row echelon form technique, the Gaussian elimination of I augmented with the inverse of A. So what's going to happen is we're going to be reducing this down into R ref. We're going to go for the identity matrix here, and in doing so, we're going to be manipulating this with the same set of elementary row operations, and that's going to put this 1, 0, 0, 1, and it's going to create a new matrix, and that new matrix will emerge as the inverse of the original matrix A. Right? So you could solve this system like we did 2 pages ago. There's nothing wrong with that. You know, if I ask you to do it using a by hand approach, I mean, we've already taken care of this approach. We've already done something like this. No need to do this one again. You could do this on your own if you want. Or you could try this technique. I think you'll find this new technique to be a little simpler. Because bottom line, you still have to go through the process of doing it by hand, where the previous one, the previous technique is going to be pretty easy to solve once you have your system set up. You still have to set up the system. This one is going to be easier to solve once you, well, maybe it won't be maybe it won't be that easier, but you won't have to put too much thought in coming up with the augmented matrix to begin with. All right, so there's a little bit of a trade-off, but it's really up to you to decide which way you like better. All right, so here I would just do -3 R1 plus R2. So 1, 2, 1, 0 staying put. But we're looking at 0. -6 plus 5 is -1. So -3. And then 1. Negate R2. And then just do a -2 R2 plus R1. That's going to give me, I'm just double checking to make sure I actually negated R2. So I have 0, 1, 3, -1. So 1, 0, negate, and I'm sorry, multiply 3 by -2, you get -6 plus 1 is -5. And then 2. I don't know, hopefully that's what the calculator said. All right, because left-hand side is now down to the identity matrix. So this is now, the way we note that is by calling it I sub 2. You'll see that in some other problems here and there. But identity matrix in 2 dimensions, because identity matrices are always going to be square matrices. So you don't have to say it's 2 by 2. If you just give me 1 dimension, I know it has to be for both rows and columns. All right. And so that's telling me that the inverse of A is equal to -5, 2, 3, -1. All right, and as a technique, I just need to know. Okay, good. Thank you. Because after all those coughing fits, I just needed a win.
I didn't plug it in, but I ran it the other way.
Right. So we have our inverse matrix. But you can see the next example is pretty much the same idea, so you can practice with that. And here what we come up with is a generalized rule that allows us to make a determination of what the inverse would be for any matrix. All right, and so if you don't do this one, that's fine. If you don't do the second one, that's okay. Definitely try this one, the one in general terms. All right, I'm not guaranteeing that that's definitely going to be on the test. But, I mean, if like my mental state right now are a seesaw, it's like, and downward is in the direction of being on the test, I mean, it's like right here. Like, it's not on the ground, but it's like right there. Like, I really want to put that on there. I don't know if I'm going to end up following through on that claim, but I mean, it's a good one. It's a good proof type question to have on a test, I think, personally. Question?
It was taken to, you're talking about the first one.
Oh, this baby right here, yeah. That juicy one.